Hi, this is my presentation for Lab 3. So in this lab, we're trying to find the distance dependence of a bar magnet's magnetic field. We know that the magnetic field follows the formula B equals kr to the n, where r is the distance between the magnet and the observation location, and k and n are constants. Through this lab, we want to find k and n. In order to do this, we are given desired x components of magnetic field due to the magnet, and we must find the distance between the magnetometer and the magnet along its axis for each value. We then analyze these measurements along a logarithmic graph to attempt to find the value n, and then we find the magnetic moment mu of the magnet. After this, we also measure one magnetic field at a 45-degree angle to the magnet's axis and compare it to a computationally calculated value. The main fundamental physical principles involved in this lab are that a bar magnet acts as a dipole, that the magnetic field of a dipole along its axis follows this equation sufficiently far from the dipole, that the Earth creates a magnetic field that we must account for, and this equation that calculates the magnetic field due to a bar magnet at any angle, not just along its axis. We use this equation as a function in the coding section. Here's a quick visual of the system. The left picture shows the system used for the majority of the lab, measuring the magnetic field and distances along the magnet's axis. The right picture shows the last part of the lab, measuring the magnetic field at a 45-degree angle to the magnet. Some observations I made during this experiment were that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here's the logarithmic graph plotting the natural logs of our magnetic field values and distance values. The slope of the graph, which is about negative 3.25, gives us our n value, and the y-intercept is the natural log of k, so we can easily get k, which is about 4.09 times 10 to the negative 7th. We now have both constants of the equation B equals kr to the n, which makes the distance dependence of the bar magnet. Now that we've found these values, we can attempt to find the magnetic moment. Based on these two equations for the magnetic field of a bar magnet, we can rearrange variables and find that k equals 2 mu 0 mu over 4 pi. By setting this equal to our value for k and solving, we get that the magnetic moment mu of this bar magnet is 2.05 amperes times meters squared. Finally, the last part of the experimental section, for the field along the 45-degree axis, I recorded an average net magnetic field of 4.61 times 10 to the negative 5th teslas. So now for the coding section. First, we input the magnetic moment that we calculated experimentally. We also made a function that calculates the magnetic field at a given location based on this formula, as discussed earlier. We then define a distance from the magnet that our observation locations will be, and we define 6 observation locations. Each is a distance 0.4 meters from the magnet, and they are in the plus and minus x direction, the plus and minus y directions, and the plus and minus z directions, one observation location for each. Now, for each observation location, we calculate the vector for the magnetic field due to the bar magnet using the function we wrote, and we make an arrow to represent the magnetic field at each location. Finally, we want to calculate and visualize the magnetic field 45 degrees off the magnet's axis. First, we make an observation location at a 45-degree angle from the magnet at a distance equal to the distance used in this section of the experiment. We then use the function to calculate the magnet's field at this location, much like we did to the other locations, and again we make an arrow for it. Here's the program's output, angled a little bit so you can see all the arrows. Notice that the two arrows that are on the magnet's axis point in the opposite direction as the others, which are perpendicular to its axis, and have twice the magnitude of the others. The magenta arrow represents the field at a 45-degree angle location, and its magnitude is larger because it's closer to the magnet than the other observation locations. So now for the lab questions. If I hadn't oriented my experiment to compensate for magnetic north, and instead had laid the meter stick at some intermediate angle, then the Earth's magnetic field would have some component acting on the axis of the bar magnet, and my measurements would have been skewed one way or the other due to the Earth's magnetic field. Depending on the orientation of the meter stick and magnet system, my results could have been increased if the Earth's magnetic field was in the same direction as the bar magnet's magnetic field, or decreased if they were in opposite directions. Either way, my experiment would not have measured the bar magnet's magnetic field precisely. Next, what if I were to stick two identical magnets together end to end and run the experiment again? Well, I would expect the two magnets to act as one larger, stronger magnet with a dipole moment with twice the magnitude. Consequently, I would expect the distance between the magnet and the magnetometer to be larger for each given magnetic field value, because the magnetic field at a set position would become larger. However, I think the distance dependence and the n value would stay about the same. In conclusion, I was able to find approximate k and n values for the distance dependence equation for my magnet, and I got k equals 4.09 times 10 to the negative 7th, and n equals negative 3.25, which is fairly close to the true value, n equals negative 3. Then I was able to use the K value to calculate my magnet's magnetic moment, which was 2.05 amperes times meters squared. At a 45-degree angle from the magnet at a distance 0.27 meters away, I experimentally got an average net magnetic field value of 4.61 times 10 to the negative fifth teslas. Computationally, for the same system, I got a net magnetic field value of 1.64 times 10 to the negative fifth teslas. I suspect that the main reason for the difference in these values is that the experimental calculation included a z component of magnetic field, even though the magnetic field at that location shouldn't have been in the z direction, and the computational calculation does not include a z component. Thanks for watching!